Mark Olwick, the Euclid image is spectacular, but where is the supermassive black hole? So this is related to a story that I shared on Space Bites last week, and that was that the European Space Agency's Euclid Space Telescope shared an image that had been taken of the center of the Milky Way. You've got this region where you've got like tens of hours of telescope time. It took 9-10 separate mosaic images that were then merged together. In this image, there are 40 million stars plus able to be like individually observed. It's the most ridiculous picture of the center of the Milky Way that's ever been taken. And you're right, the supermassive black hole at the heart of the Milky Way is in that picture. But why can't we see it? Where is it? Why isn't there just this giant swirling disk at the center of this picture? And the reality is that the supermassive black hole, or the reality is that the heart of the Milky Way is obscured from us. And this is a problem that has plagued astronomers for centuries. And so when you look out into space, you can see in all directions, but the place you must not look is at the sun or at the disk of the Milky Way. And in fact, astronomers have a term for this. They call it the zone of avoidance. And that is that there's so much dust mixed in at the center of the Milky Way. We are embedded inside the Milky Way, and we're trying to look through multiple spiral arms down into the center of the Milky Way. Well, those arms are getting in the way. And so any of the stuff that's in there down at the center is obscured from visible light telescopes. And this has been a problem for a long time. And it's only in the last couple of decades that astronomers have finally been able to look through all of that dust to see what's in there. And you need to use a different wavelength. So you can use infrared. You have to use very specific wavelengths of infrared. And then there's other wavelengths of radio waves that will get you in to look at stuff that's inside, passing through the dust. And this was how astronomers even confirmed that there is a supermassive black hole at the heart of the Milky Way, which was that they had to build these infrared instruments, and then they were able to see these stars that were orbiting around nothing at the center of the Milky Way, almost like comets going around the sun, but if the sun wasn't there. And when you do the math and you calculate the motion of these objects, of these stars, full stars that are going in these comet-like orbits around the center of the Milky Way, you were able to infer that there was an object there, and you can calculate the mass. And that is the supermassive black hole at the heart of the Milky Way. And we can see these supermassive black holes at the hearts of almost every galaxy that's out there, thanks to these new techniques, infrared, radio. They can even detect them in X-rays. But let's imagine that we removed all of that dust, and so it wasn't obscuring the supermassive black hole from our perspective. Would you be able to see it then? And the answer is no, because it's actually not very bright. It is not actively feeding right now. And so the occasional, I think it's like a couple of times the mass of the Earth are accumulated in the supermassive black hole every single year. And so black holes can be actively feeding, or they can be quiescent. And the supermassive black hole in the Milky Way is in its quiescent phase right now. And so we just aren't able to see it with our eyes. And in fact, you can't even see it with a regular telescope, no matter how good your visible light telescope is. Say Euclid, a space telescope that's been staring at this area for tens of hours, it still isn't able to see it. Now, if the supermassive black hole went quasar, in other words, if it went into this phase where it was actively feeding, say in the future when we merge with Andromeda and fresh new gas and dust is forced into the center of the Milky Way, maybe those stars, some of them are then kicked into the black hole itself, and the black hole kicks into full quasar mode and starts to blast out radiation. We still won't see it because of all of that dust. And so it'll be completely obscured from our perspective, embedded in the disk of the Milky Way. It's only when you are outside of the Milky Way, able to look directly at where the quasar is blasting out material, can you actually detect it. But the astronomers, with their infrared, with their radio waves, with their ability to detect X-rays, gamma radiation, they would detect its present. Now, if you removed all of that dust from the Milky Way and yet somehow could still feed the supermassive black hole, then you could see it. Then it would be pretty bright. It would be on the order of the brightness of a star. in the sky. So when you look at all the stars, one of those could be the quasar that is the supermassive black hole at the heart of the Milky Way that is actively feeding on material, and someone has conveniently removed all of the dust from us to it. But yeah, that's why we can't see it. And that's why we want to be able to look in other wavelengths like infrared and radio waves. Okay. Hey everybody, welcome to the final live question show before I go on hiatus. So this is the last one. Make your peace. So this will be 2 hours long, and I will answer all of your questions about space and or astronomy. And then this will be chopped up and turned into the question shows that we release every single week. So go ahead. I can see a bunch of questions have already gone into the questions already. So let me explain the hiatus part first, and then we'll kind of go into the rest of it. So every year, and this, if you're new around here, this surprise is that I stop live streaming my regular shows for July and August, and we stop recording Astronomy Cast. And there's some other stuff that I do that I stopped doing during July and August. And it's mostly just because trying to make my way to if I want to go traveling, I still have to find high-speed internet. Like I spend 10 months a year trying to make sure that I can always get access to high-speed internet, and I can keep the show going week after week after week. And then I can sort of then go on hikes, I can do stuff and not have to worry about where I'm going to find high-speed internet. And it's just like, it's good to refresh the tank, to remind yourself why you enjoy this kind of stuff, so that you're just, champing at the bit to get back at it when I come back from the hiatus. Now, this summer is going to be a little bit different because I am working on a totally new project, which I've been demoing a couple of times. There's one on the channel already, which is my smart telescope. And this is a sort of custom built, homemade smart telescope. So similar to the Sea-Star or the Vespra or the Dwarf or all of these like automated smart telescopes, I've got a version of that is built with sort of higher end parts, and it is lightning fast and has incredible optics, and it's super easy to use, and it's live stream ready. And it's really cool. And I've been showing off sort of the incremental steps bit by bit by bit. And now every time there's clear skies here on the west coast of Canada, which is rarely, I am generally doing a live stream. And so I've been doing a couple of live streams every week in the last couple of weeks. And things are getting really good. Like, I'm so happy with how this thing is performing now. So while the question show is going to be gone, you're probably actually going to get more live streams out of me over the next couple of months, but they're going to be me testing out the telescope. But I'll be gladly answering your questions about space and astronomy and talking about telescopes and observing and if you want some space dad advice, that'll all be on the table. And we're still going to do Space Bites. We're still going to be releasing question shows. I'm still doing interviews. So the only thing that's really changing for this channel is that I won't be doing this 2-hour live stream every Monday until the beginning of September. So get that out of the way. The next thing is to sort of talk about the format of this. So, for those of you, this is your first time. I try to give emphasis to the people who have never had a question answered before. So if this is your first time, then definitely ask your question. And I think you'll be delighted that I focus on your question above all others. The other thing is that just remember that I am a journalist, not a scientist. And so, I'm not great. I cannot give you opinions about scientific matters. I can just be I can communicate the scientific consensus of everything that the current scientific community believes. And then, there's going to be all kinds of reasons why I don't answer your question. Like there are too many questions. I can't get to it. I don't know the answer. Your question requires some math, or it's a question that we've just answered a lot in the past. So, it may be like, oh, I know the audience is going to be like, this one again, Fraser, why don't you believe in aliens? That kind of thing. So, okay. Awesome. All right, let's get into it then. Let me find a good question. I don't know what my keyboard is. I forget. I got it. It's a key. Now I gotta put on my glasses. Key chronon? Yeah, all right. Okay, Michael McConnell. What keyboard do you have? Is customized at all? It sounds very satisfying, almost as nice as mine. So this is my keyboard. And it's a key chronon. And so it is kind of mechanically, but it's also like a USB keyboard, but it's also a Bluetooth keyboard. And it's sort of compact, sort of fits on my desk. I don't have a lot of space on my desk. So that's the one that I got. I like it a lot. And they make a bunch of sort of different variants, one with the big number keys on as well. I don't need the number keys on mine. So yeah, they're very good. Ed Skeptic. What created the fields and quantum fluctuations that supposedly set off the Big Bang? We have no idea. Nobody knows. Nobody knows what set off the Big Bang. That, astronomers look out into the universe today. They look and they can see that galaxies are moving away from us in all directions. And in fact, galaxies are moving away from each other in all directions. Space is becoming less dense over time, which means that if you run the clock backwards, space would be getting more dense over time. And you can then calculate when were the things that were on the right side of us that are now 42.5 billion light years away from us, and the stuff that's on the left side of us, it's now 42.5 billion light years away. I hope I did that right for you, by the way. I did these flipped around. Anyway, this is my right. But anyway, yeah. So the stuff that's 42.5 billion light years to the one side of us and the stuff that's on the other side were once in the same location. And when you do the math, that number comes out to 13.8 billion years ago. And we know, again, when we do the math, we know that all of that material was once so close, it was kind of like the surface of a star. The sort of the density of the surface of the sun, for example. And that you would expect that this would be this place that you could see out in the universe at this time. And what do you know? We have the cosmic microwave background radiation. So that verifies that the universe was once at that density. But you can keep going and you can say, well, if the universe was expanding, then there was going to be this time when the entire universe was kind of like the interior of a star. And now a place that is so hot and so dense that you've got hydrogen turning into helium. And then you just have to calculate what is the percentage of hydrogen to helium, and that will tell you when that happened. And the percentage is about, say, 75% hydrogen, 25% helium. And you can calculate that, in fact, now we're back to just a couple of minutes after the beginning of the universe. And for like a dozen minutes or so, the entire universe was like the interior of a star. But physicists have these giant particle accelerators, so they can go even sooner. They know that at a certain point in the universe, various forces that are currently separate today, the strong force, the weak force, electromagnetism, gravity, were once combined forces. And they're able to, prove that this was the case in the Large Hadron Collider. And that gets you down into the first few just sub-seconds after the Big Bang, when the strong, the weak, and electromagnetism were all one thing. Electroweak force? No, there's another. Anyway, yeah, we still don't know how gravity works, but so on. And that allows you to kind of calculate this moment where all of this expansion began. But, and then there are some problems with the Big Bang. And so scientists have come up with a framework called inflation that explains some of those problems with the Big Bang. And that helps get you even closer to time equals zero. And in fact, there is observational evidence that this inflation period happened in the universe. But what happened before time equals zero? We don't know. What set these events in motion? We don't know. And we may never know. It could be that this is just a wall of our knowledge. Maybe when scientists figure out how gravity interacts and, there's a quantum theory of gravity that fits well with the other forces, that may get us a little bit closer. But whatever were the conditions that began this whole process, it is probably wiped out by the Big Bang itself. When you think about, imagine a hard drive, and you just go and you write ones and zeros into every single sector of the entire hard drive, and you completely wipe it, and then you put new data inside of it. What came before that? Well, you don't know. That data, those data are gone. And, maybe if we're super lucky, there's some kind of echo in the universe today that we can then look at and say, okay, maybe that these were the conditions that led to the universe as we understand it. But, it's entirely possible that we will never know the answer to this question, that for the rest of intelligent civilizations from now until the end of the universe, or until the heat death of the universe, 5 quadrillion years from now, in some classroom, someone's going to ask, what came before the Big Bang? And the teacher, probably a robot teacher, is going to say, we don't know. We have no idea. And that's okay, right? Like, I think that there are a lot of people who that is a very uncomfortable thing to hear, that they need an answer, and there has to be an answer, and that answer has to be knowable. And that there are all kinds of mythologies that have come up to try and explain what might be the unknowable. That, when you sort of consider the Greek mythology or other mythologies, the Norse mythology, they come up with answers for, like, where did the universe come from? And because we don't want to hear, we don't know. But sometimes we don't know is the only answer you can go with. And you can follow that with, like, let's find out. But yeah, we don't know. Nomad77. Considering our black hole is only 4 million solar masses, is it really supermassive? Well, compared to a stellar mass black hole, it is definitely supermassive. When a star with more than 20 times the mass of the sun goes supernova, it will leave behind a black hole. And, those black holes will start out in this sort of 3 to 4 solar mass range and then grow from there. And so on the one hand, you have the ones that are 4, 10, 20, 100 at the most times the mass of the sun. And then you've got, the Milky Way is one, merely 4.3 million solar masses. You've got Andromeda's, which is about 100 million solar masses. But then we see examples of supermassive black holes out there with hundreds of millions, even billions of times the mass of the sun. So they can get very massive. But I still think that 4 million is a lot and qualifies as supermassive. The interesting sort of search is the ones that are in the middle, the intermediate mass black holes, the stuff that's in the thousands of times the mass of the sun. You would expect that those would be out there. And when you sort of consider the mass distribution that is very common, when you look at stars, there are a few stars that are very massive. Most stars are small. You would expect to see more of the black holes that are in that kind of middle range, but we don't. We see the ones that are a couple of times to 100 times the mass of the sun, and then we see the supermassive ones. But where are all the ones that are intermediate mass? Richard Gould, are the interviews on a different or new podcast feed? I haven't got an interview other than Anton on Patreon in forever. There should have been one that came out last week on space food. So there was a break in interviews when I went to Japan, and so I'm doing new interviews now, and so you'll see those new interviews in the feed coming soon. So stay tuned. Whole bunch more interviews coming. The Linthus. What would be the challenges, advantages, and consequences of pushing the International Space Station into a higher orbit instead of deorbiting it when it gets retired? Yeah, this is a very tricky subject because there are a lot of moving pieces here. So as probably everybody knows, NASA is planning on deorbiting the International Space Station by around 2030. And the Russians may disconnect their section of the space station before then. There are some private partners that may attach sort of private modules to the International Space Station, and then those might be detached before the station is dropped into the ocean. And so parts of the space station might survive after 2030, but we'll just go with this sort of the baseline expectation that around 2030 there's going to be a tug from SpaceX launched to dock with the space station. It's going to fire its engines and it's going to drop the entire station in through the atmosphere and drop it into this was it Point Nemo, the like the farthest place from anywhere in the Pacific Ocean, to minimize the chance that anyone's going to get hit, because it will survive. Like chunks of the space station will absolutely survive, make it through the atmosphere, crash into the ocean. And so you're saying like, oh, like what a shame. And you're exactly right. It is a giant shame that this hundreds of billions of dollars, or definitely more than $100 billion piece of equipment, probably the most complicated machine that humanity has ever built, are, you know, the West's only operational space stations. Like the Chinese have theirs, but once the International Space Station is gone, only the Chinese will have a presence in, you know, permanent presence in low Earth orbit. That sucks. So why not keep it? And there's a couple of issues. So the first thing is that NASA is not giving the budget. So, I'm kind of torn to think of a really good analogy, but, let's say you're staying in a really nice apartment and you can't afford the rent anymore. And someone says, well, why don't you just stay there? Well, like, I can't. Like, why don't you just stay? Well, because I don't have the money. Yeah, but you just stay. Well, you know, like, it's not allowed. So the problem is that the budget for NASA is being reallocated to other priorities. The White House has put its priorities, Congress has made its priorities, and the plans are sending humans to the moon, sending some missions to Mars. There's a bunch of other stuff that's in the works, and it does not include the billions of dollars it costs every year to maintain the International Space Station. That's sort of like the big thing. It's just like nobody is willing to pay for the cost to keep it operational. So now what you're saying is, well, why don't we just raise the orbit? And that is absolutely possible. You know, the tug that is going to fire its engines and lower the space station's orbit could fire in the opposite direction and raise the space station's orbit. And in fact, the space station raises its orbit all the time. There are regular cargo vessels that dock with it, deliver more propellant. The cargo vessels can help raise its altitude. The station itself can raise its altitude. Like, this is a maneuver that has been done for a long time. But again, if there's no budget being put into it, then these cargo vessels will no longer deliver propellant to the station, that this process will end. And so it's going to go. So like, that's like the answer is always money. But there are a couple of other issues, which is that, you know, it's an old machine. And that a lot of the time spent by the astronauts when they're on board the station is maintaining it, swapping out parts, fixing the things that are breaking, and just keeping this machine going. It is, you know, it's not just a house that gets better with time. It's a 30-year-old piece of flying machinery that has all of these subcomponents, and they're all working all the time. Things that circulate air and heat and pressure, and all of this stuff is going on nonstop. There's pumps, there's all of the solar panels, there's the radiators, airlocks, like just scientific equipment. So much is going on in this thing, and it all requires maintenance, and maintenance requires money, and there is no money. So I think, you know, in my perfect world, they would maintain the International Space Station. They would raise its orbit, and then they would just add on to it, just bit by bit by bit. Like, you've got this place, it's permanent, and you can just keep adding new modules to it. You can drop other modules off of it. The space station is more like the ship of Theseus, where it is this place in space where stuff happens. And whenever you want to launch a new part to it, you've got this established base that you can do that. Launch a new module that has the most modern technology. Then, by all means, ditch an old module that is just so cranky and you're having to carry its weight all the time. Drop it into the ocean. Keep going. So I think if there was unlimited money, or if there was even adequate money, that would be the solution. You constantly have this nice, stable, you know, beachhead in orbit that you can continually use, because as soon as the station comes down, then there is no safe place that you can go and build up again. You're gonna have to launch an entirely new station to begin again. And if you've ever been through this process, like once you don't have a place you can work from, it's so much harder. So yeah, the right move is to continue funding the station, to sort of imagine this as this forever station, this ship of Theseus, just swap out the parts forever. And 1,000 years from now, the bits and pieces of the International Space Station will be embedded within this larger station that is just to maintain this permanent presence in orbit. Dougal, do you make plans on what to do while on hiatus? No plans. I'm not a planner. I don't plan. Billions and billions of stars. Are the little red dots supermassive black holes inside galaxies? That does appear to be what little red dots are. There's been this ongoing scientific question about the little red dots since James Webb first discovered them. In fact, it was one of the most dramatic new things about the universe that James Webb had turned out. Like right now, if you said, what is the biggest thing that James Webb has found? It's the little red dots. And these are these weird, almost point source objects that are giving off an enormous amount of radiation, but it's all in the red. And they're seen within the first billion years or so after the Big Bang, and then we don't really see them after that. And whenever you see something that is giving off that amount of energy in a very constrained, very tight location, then you assume that it is probably, has something to do with a supermassive black hole. The size definitely matches. These things are in the order of tens of light years across. So they're very, very small. And yet they are pumping out enormous amounts of radiation. But there's one big missing problem. And that is normally when you see supermassive black holes, especially actively feeding supermassive black holes, they're giving off a lot of X-ray radiation. The accretion disk around the black hole is so compacted together that it's almost like the interior of a star. So fusion is happening around a black hole, just in the accretion disk. And that gives off X-ray radiation, and X-ray telescopes are the way we find many of these supermassive black holes. But these little red dots aren't giving off the X-ray radiation in the way that you would expect. And so there's been lots of other ideas. My personal favorite is that these are baby globular star clusters in formation. That would be really cool. But there's been a bunch of ideas. But recently, probably in the last couple of weeks, astronomers have found an example of a little red dot that is giving off some X-ray radiation. And what they think is happening is that these sort of new supermassive black holes are feeding on so much material. They're producing so much dust around them that the dust is obscuring our view into the X-ray radiation. We're seeing the light come out, the red and the infrared light coming out of it, but we're not seeing the X-ray radiation that you normally associate with a supermassive black hole. So that's kind of the leading theory right now. And what's even more interesting is how the evidence is building for this idea of direct collapse black holes. So, one of the longstanding questions about the universe was like, what came first, the galaxies or the supermassive black holes at the centers of them? That, in one case, you could have this giant supermassive black hole, and that could serve as a kind of anchor for other material to start to go into orbit around it. Or you could have like a whole bunch of stars, the stars go supernova, the turn into black holes, the black holes find each other, they merge, the black holes feed, and you get this accumulation of black hole at the center of this galaxy at the same time that the galaxy is forming. And there was kind of the bottom up versus the top down, and there was two camps. But the real kind of general consensus is that no, they go hand in hand. That isn't it weird that the supermassive black hole and the galaxy around it are kind of roughly similar to each other in scale. There's got to be some kind of relationship, but it is really starting to look like it's the black holes came first, and that that there could be ways that you could get a black hole that is millions of times the mass of the sun, not by merging black holes, but just directly, that there's a giant cloud of gas and dust, some way of material gets funneled into this central area and it just turns into a black hole. And that would be groundbreaking. Like, that would be Nobel Prizes if we can get to this place where they know this kind of thing for sure. But it's sort of where things seem to be indicating. So it's a really exciting time. William Hallman, why are there not 3 or 5 space stations? Money, budget. The Indian Space Agency is planning on launching the Indian Space Agency is planning on launching their own space station probably by the end of the decade. And then that's going to be a stepping stone for them to go to the moon. So it could be that there will be a Chinese space station and an Indian space station, and then maybe a couple of private space stations. There's a couple of companies that are quite well along. One company called VAST. And so we might get to a place where there's a few stations, maybe 3 to 5 stations as you're hoping. One from the Chinese, one from the Indians, and then several private ones. Maybe 2 US private ones and 1 European private one. Luis Carniero. About the invisible black hole in the Euclid image, will Euclid plus James Webb data force a revision of dark matter models, or could something unexpected emerge? Right, so the whole purpose of the Euclid mission was not to take this amazing image of the center of the Milky Way. It was to use this pair of instruments to map out the history of the universe, its evolution. So it has this visible light telescope, so very similar to the kind of observatories you're probably familiar with. And that allows it to measure the shapes of galaxies. And then it has this infrared instrument on board as well, which allows it to measure the chemical composition of these galaxies. And so it can put these two things together, and it can measure the shapes of the galaxies and the composition of the galaxies. And what astronomers are looking for is they're looking for gravitational lensing. So we know that when you have large amounts of mass in between you and something that you're looking at, then that mass acts like a natural lens that subtly distorts the shape, the pathway that the light is taking to get to you from those more distant objects. And so Euclid is doing this just giant survey of a huge swath of the sky, but it's taking long images. Like, it's really staring at each spot in the sky for long periods of time, long enough that astronomers can start to detect all of that warping caused by the matter that's out there. And that is the dark matter, right? The dark matter is invisible, and yet astronomers can detect how it warps stuff that is behind it. The example that I always use is that you're down at the bottom of a pool. You're laying on the bottom of a pool and you're looking up and you're looking at trees or people or whatever, and they're all, all refracting around, distorted, because you've got the water in between you and those people. And the dark matter acts like this thing that's warping the light that is coming to our eyes. And Euclid will allow astronomers to look back into time, because, of course, the farther away we look, the earlier we're seeing back in time, and really measure the concentration of dark matter at different points in the universe. Measure the influence of dark energy on the expansion of the universe at different times in the universe. James Webb is not a survey telescope, and so it can't do these wide field views of the sky. It can be directed at specific targets. Nancy Grace Roman is a lot more like Euclid. It's going to be doing these wide surveys of the sky. Vera Rubin is doing these wide surveys of the sky, watching how things change. So there's a bunch of instruments that are doing this same job, and they're going to try and all approach this problem from different perspectives. But Webb is when you found something unusual and you want to get really good images of it, you call on Webb. In the same way that you call on Hubble, right? Hubble is like looking through a straw. it doesn't have a very big field of view. And so when you've got a specific target, you want to look at a newly forming planetary system, you want to look at a very specific star, you call in Webb or Hubble. But if you want just a wide view of the entire sky, that's what you're doing with Euclid. And these surveys are going to help us understand what is the influence, what is the percentage of dark matter in the universe, how has dark energy changed over time, if at all. Perry, if we could put a 1 Tesla magnetic, oops, did I lose that? Did I lose that? Okay, all right. Okay, if we could put a 1 Tesla magnetic dipole at Mars L1 Lagrange point to encompass Mars and a magnetotail, wouldn't that be a good precursor to eventual colonization? Yeah, if you could put a 1 Tesla magnetosphere around Mars, then there would be all kinds of good things that would happen for Mars habitability. So the big thing is that, you know, Mars is bone dry today, that the amount of water present on Mars is very low in the atmosphere. We can see that there are polar ice caps, and those ice caps contain water ice with carbon dioxide on top of it. And astronomers, the missions have gone to Mars and have dug into the regolith and determined there is, in fact, water mixed in with the regolith on Mars. So there's no water. It's that there's no water that's kind of available in the atmosphere, and that the atmosphere is very thin. And the other issue is that there's carbon dioxide, probably methane, other gases. They would just thicken the atmosphere and thicken it and thicken it and thicken it. And, you know, eventually it would get to the point where liquid water could actually exist on the surface of Mars. Now, you wouldn't be able to breathe the atmosphere, be carbon dioxide, but it would be thick enough that the water would melt, that you would actually start to get standing water on the surface of Mars. And that's just by blocking the solar wind. But what you're proposing is a mega engineering project beyond the likes of which we are able to do. We are not able to generate a magnetosphere at a planetary wide scale. It's just like you need to turn the center of Mars into liquid, you know, a dynamo in what the Earth has. But there is an idea that I like that's sort of on that same pathway, which is that instead of trying to surround all of Mars in a artificial magnetosphere, you just need to block the solar wind from getting to Mars. And so you could put an artificial magnetosphere at the Mars-Sun L1 Lagrange point, so the point in between the Sun and Mars. And it can be much smaller. It doesn't have to be gigantic. It just has to be big enough to essentially cast a shadow, a solar wind shadow on Mars. And now Mars would be protected from the solar wind. And then these volcanic gases would start to replenish the atmosphere on Mars. Now, that still wouldn't protect you from the cosmic rays. So, and they are the more dangerous ones. So, we talk about these radiation hazards that you get when you're out in space. Like when you are away from the Earth's magnetosphere, you are going to be getting about 200 times as much radiation on your body as you do when you're down on the Earth. And so, being outside on Mars is just very, very bad for radiation. You would be blocking the solar radiation or the solar wind particles, but they're minor. They're not that bad. It's the cosmic rays. They're coming from all directions. You know, these are accelerated by supernova and quasars and gamma ray bursts and who knows, pulsars, and that they are still going to strike the surface of Mars. And so you're still going to need radiation protection. It will get better when the atmosphere on Mars thickens, but it will never be safe. It will always be a place that you're going to spend. Like you think about getting a sunburn is bad, right? You just put on some sunblock and now you're okay. Well, there is no sunblock for cosmic rays. So you will be sort of counting every second that you have to spend out under the sky on Mars. Is there a buffering? Welcome back, Stanton. Sorry about the buffering. Use a keyframe frequency of 4 seconds or less. I don't even know how I make a keyframe buffering. This is brand new. I'm sending out super high speed data. Let me just check my settings. I would have to cancel. I don't see where I have keyframes coming in my video output. So I can downgrade the resolution from 4K down to 1080p. But it's 4K 60 frames a second. So there may be more buffering. I apologize. This is a totally new problem. I've never seen YouTube say this before. Yeah, so if there's a problem, just refresh the browser. It'll be back. Gooeyble? Regarding the accretion disks, do stuff near the black hole spin faster than stuff that are more distant, or dark matter influences it too, so everything spins or at the same speed? So the question that you're asking is this idea of the speed that stars move inside a galaxy. And this is sort of one of the indications that whatever is the mass of the galaxy, we can only perceive a fraction, like 10% of the mass of the galaxy. And so this is the kind of the thought experiment. This is the theory that it sort of explains this. You know, there's a bunch of independent lines of evidence for dark matter, but this is one of them. And that is that when you think about the solar system, think about how fast Mercury is going around the sun. You know, Mercury is about 48 kilometers per second. Earth is going 30 kilometers per second. Neptune is going 5 kilometers per second. So Mercury is going around and around and around. Earth is going more slowly around. And then Neptune takes, 170 years to go around the sun. And so if a galaxy is the same thing, but just at a vaster scale, then you would expect the same thing, which is that when you look close to the center of the galaxy, you would see stars that are zipping around the galaxy. And then when you go further out, you would see that the stars are going a little bit more slowly. And then when you get all the way out to the edge of the galaxy, the stars are going to go extremely slow. But that is mostly not what happens. For the vast majority of the stars in a galaxy, they are all going the same speed. So they're all going the same orbital speed around the galaxy together. And so it's not like the solar system where you've got all of these stars and they're all going on different tracks. You know, imagine you have a bunch of racetracks and the cars are going different speeds around the racetrack. The close one's going really fast. Farther out, they're going a lot more slowly. And not just because it's taking them a lot more time, but they're literally going more slowly. So you've got a race car close in and you've got a person walking on the outer edge of this. But with a galaxy, it's more like a plate is spinning or a record. The whole thing is just turning. And all the stars are moving at the same speed. And you just would not expect that. You would expect that they would be more like a solar system. And so the only way that you can get that motion is if the galaxy is actually embedded within something that is way bigger. And this whole thing is just kind of spinning, right? Slowly rotating. And that is, 10 times the mass of the part that we can see. Now you get this motion as expected. But it is not entirely the same speed. In fact, there is this point, this cliff inside a galaxy. And once you get closer in, then the stars do actually kind of behave like you would expect in a solar system. So normally it's this smooth slow down in the solar system, but in a galaxy, you get this They start very, very quickly orbiting around the center of the galaxy. Then they slow down, and then you get everyone from that point outward. Everything is orbiting at the same speed. And when you think about the discovery of the supermassive black hole at the heart of the Milky Way, about 20 plus 30 years ago, astronomers were able to finally observe through the gas and dust and actually see what was going on at the center of the galaxy. And they saw these stars that were in orbit around nothing, right? Around this supermassive black hole, but you can't see anything there. And so, yeah, when you're really close to the center of the galaxy, then things actually do move very fast. And we see this in other galaxies as well. Norway Island. Where is this? Apologies. Zephan. I saw there was an island off Vancouver Island for sale called Norway Island. Ever been there? Is there a Sweden Island next to it? So Norway Island is a 30-acre private retreat located in British Columbia's Southern Gulf Island, situated between Gabriola and Thetis Island. Has a 60-foot dock, power, 3 homes, including a 5,500 square foot residence. Let me look at this place. Whoa. So, and how many acres is it? 30 acres. Okay. So, I've never been there. So where I live on the west coast of Vancouver, I live on Vancouver Island, but Vancouver Island is surrounded by a whole bunch of smaller islands. These are called the Gulf Islands. And I actually grew up on one of the Gulf Islands called Hornby Island. And so every day I would have to catch 2 ferries and 3 buses to go to high school. So I would get up in the morning, ride the bus to the ferry, ride the ferry, get on another bus, get on another ferry, get on another bus, and go to school. And then do the same thing coming home. So I'd leave my house at 7 in the morning, and I would be home by 5. That was my day, every day. And then I ended up moving to the city where I went to high school in. So now I live in this city called Courtney, which is where I used to go to high school. And our Hornby Island is much bigger. I don't know how many, like it's thousands and thousands of acres. But, these little islands come up for sale all the time. And like, if that's your thing, I guess, I think having grown up on an island, and a fairly, there was like 1,000 people living on the island. Our property was 5 acres on Hornby Island. And my wife and I, we were kind of wondering, like, do I want to live on the island again? The small island. And our dog got sick, and we just had to wait. Like, you just have to wait till the next day. You can't go see a vet. You can't go see a 24-hour vet. You just got to wait until the ferries are running. If somebody has a heart attack, you just got to wait. If you're lucky, they'll bring in a helicopter, but mostly you just wait. And the expense and the hassle is off the charts of just trying to get stuff delivered, or you got to go buy stuff in town, and then you got to ride the 2 ferries, and it takes an hour and a half to go get supplies if you want anything you're not going to buy from the little store on the island. So yeah, I would, for some people, I'm sure that feels like it's the dream, but instead, if you want to just simulate it, just, don't leave your house. You could probably cordon off a chunk of your house if you have a detached home, maybe you've got a 1/2 acre, 1/4 acre that you live on. Imagine you're living on an island. And then as soon as you're like, man, I want to go watch a movie or go to the restaurant or get some groceries. Now imagine, stand at the side of your property for 2 hours, and then you can leave. And that's what it's like. Luis Carneiro, Fraser, you need to visit Portugal. I'd love to visit Portugal. All right, here's a good one. Henry Warren, what is the best way to watch a SpaceX launch? The best way to watch a SpaceX launch, I guess, you can watch it on X, I guess. But if you want to watch one in person, it's actually a very achievable dream if you want to watch a rocket launch. And now there are so many rockets launching from Cape Canaveral. It's actually a very doable thing to do. So what you do is you look for hotels in a place called Cocoa Beach, which is just outside of Cape Canaveral, just to the south of Cape Canaveral. But it's like a nice resort town on the coast of Florida where you can stay in a hotel that will have a view of the ocean and will literally give you a view of Cape Canaveral. You can sit on your hotel and you can see rockets on the launch pads out at Cape Canaveral. And so when the rockets take off, you can just be sitting there on your, down on the beach or just on your hotel balcony, and you can watch these rockets take off. And if you want, you can go to Cape Canaveral, to the Kennedy Space Center, which is, several miles to the north of Cocoa Beach, and there's better facilities, and they do these big launch watch parties where you can join thousands of other people in these stands and watch these rockets take off. So it's a great experience. And we're at this point now where multiple rockets are launching, sometimes every single week. And so you don't have to choose them with such precision anymore. You can just kind of go, and there will be a SpaceX launch. It's going to happen. So what you do is you book a flight into Orlando, and then you just rent a car in Orlando, and it's about an hour drive from Orlando to Cocoa Beach. There's another town that's even closer, but it's not as nice. Titusville. So there's another town called Titusville that's just outside Cape Canaveral. Cocoa Beach is sort of nicer, but both will do. You can rent hotels in either one and watch a rocket launch. And so it's, you can pick up the hotels on discount sometimes if you get a travel deal. The flights to Orlando are not that expensive, depending on, you can stop at Disney World while you're there. You can drive down to Miami if you want. If you've got a little extra time on your hands, you've got a rental car. It's a great time. And so I would say, for most people, you could probably do a trip to Cape Canaveral, see the, once you're Cape Canaveral, they've got the space shuttle, is it Discovery? I think it's Discovery. I think Discovery is at Cape Canaveral. They've got a Saturn V rocket that's in this giant building. You can see they've got a moon rock you can check out, and then you can take tours of the actual rockets that are there. You can see the vehicle assembly building and go into all these historic sites. It's an incredible place. And so if you want like a really fun holiday with a chance to watch a couple of rockets take off, definitely consider doing that. Yeah, it's super achievable. It's, when I think about the sort of people's bucket lists of things they want to do someday, and if you live anywhere on the East Coast of the United States, then you can drive, right? You can camp. It's not that hard. And you get to watch a rocket launch, which is so cool. Everyone should watch a rocket launch once in their life. Now, if you don't live in the US, then you've got, a much more difficult journey ahead of you. Nomad, any chance of a shout out to the Canadian men's World Cup team for their recent successes? Yeah, we're in the final 16. So this is awesome. And it's very cool. I got to say, I was a little bit sort of anxious about, all of, the US and Canada and Mexico hosting this event right now. But it's gone great. And I think the thing that's wonderful is that each of the teams choose a home city in the country, and there's been just a great sort of outpouring of support for all the different teams that have set up shop in all of these different cities around the United States and Canada and Mexico, and then all these nations are competing, and it's just shows you how humanity can come together in these wonderful ways, that once you get to know people, you can be friends with them. You just have to meet them. You just have to get to know them, as opposed to the kind of xenophobia. Like, instead of having wars, let's play soccer. How great is that? How's that? Dougal, do you think it would be feasible to use just a long tether as a power source for a spacecraft orbiting around Jupiter's strong magnetic field? So, wherever there are moving particles, there is energy. And so theoretically, if you had a spacecraft that was in orbit around Jupiter and it was moving through the magnetic fields of Jupiter, there is some way that you could extract energy out of that process. Whether you would be harvesting the currents that are generated by the interactions with the magnetic field, or whether you were trying to harvest the particles that are crashing into the spacecraft. There's like some way, whenever there's motion, whenever there are fields, whenever there's magnetism, there's energy to be harvested. But it would be so hard, and it would be very little, and it just wouldn't be efficient compared to solar panels. We know that solar panels work at Jupiter. Now, they have to be 1/25th as much power for the same size. So Juno, if you look at the Juno spacecraft, it's got enormous solar panels. Same thing with the upcoming Europa Clipper mission. Huge solar panels. And that is because you've got 1/25th the sunlight on Jupiter that we have on Earth. And so you just need 25 times as much solar panels, but it works just great. And solar panels are just like the nicest, stablest, safest, dependable technology. People are even working on solar panels for Saturn. In this case, you need them to be, and I forget what the number is, like 100? Like Saturn gets 1/100th the light that the Earth does, and yet solar panels would still theoretically work out at Saturn. Oh, yeah, there you go. Yeah. Evan.pro, Atlantis is at Kennedy Space Center. Yeah, yeah. And there's like a really great Canadarm just right there. You can check it out. Nomad, are you following Nordspace and their new launch facilities in Newfoundland? Did you notice that Nordspace is one of the patrons that I say their name at the end of every episode? So they are supporting us. I'm definitely following what Nordspace is up to. I can't wait to check out what's happening in Newfoundland. So for those of you who don't know, there is a Canadian launch complex being built on the east coast of Canada. Now, obviously, if you want to launch into sort of an equatorial orbit, the best place to launch is close to the equator. That's why, you launch from Florida. It's as far south as you can get in the United States, except for Hawaii. But anyway, in the continental US, Florida is the farthest south, the closest to the equator. And the Japanese do kind of the same thing. But if you want to launch on polar orbits, then you don't need to be close to the equator. You can kind of launch from any point on Earth because you're trying to go above the poles. You have to cancel out the Earth's rotation anyway. And so there's a new launch complex that's being built in Eastern Canada. I think it's in Nova Scotia, not Newfoundland. But yeah, I will definitely try to get out there and get a tour of it and see what's happening whenever I can kind of get that organized. And thanks for your sponsorship, Nordspace. Zach Diecast Mansour, I know we'll never send a generational spaceship of people to another star anytime soon, but do you think we'll send a generational probe to one that multiple generations track to another star? Well, first, never say never. That the future of humanity, we hope, is going to be long, and there will be interesting technologies that will be developed, and that we have no idea what future generations will accomplish. And so this idea of a generation ship, this is, because it takes so long for us to be able to get to another star system, people said, well, why don't you instead just take the time, and instead of trying to complete the journey in a ridiculously short amount of time, instead send a generation ship, something where people live, or people are born, they live, they die, they're born, they live, they die, multiple generations for a ship to reach another star system. And this is a trope in science fiction. I think in the Orville they found a generation ship, and of course that highlights the downside of the generation chip, which is that future technology may be able to get you to your destination faster than the generation chip can go. And so wouldn't that just be sad that you are the third generation, you've been living, your family has been surviving, trying to get through day to day as the technology is failing. And then, a brand new sleek spaceship from Earth shows up and says, hey, do you guys need a ride? We're off to Alpha Centauri. You're like, oh, why did we even do this? Why are we even here? And that is that is always the challenge. But what you're describing is when we send a generational probe that has multiple generations tracked to another star. You're describing a von Neumann probe. You're describing a self-replicating robot probe. Also a trope in science fiction. My favorite of this is We're Legion, I Am Bob, which talks about a guy who gets turned into a von Neumann probe. I won't say anything more, except that it's one of the best sci-fi book series about this kind of thing I've ever read. It's super entertaining. So, will we do this? Well, the technology to create a self-replicating robot probe, although is beyond our capability today, a lot of the pieces are coming together pretty quickly. We are developing better examples of harvesting materials out of rock and regolith and things like that. And 3D printing is coming along, getting better and better. We can 3D print in so many different materials now: titanium, steel, ceramics, glass, plastics. Like, it's kind of amazing. And even people are starting to envision ways that we can 3D print or produce electronics in space out of raw materials. So although it's beyond us today, a lot of people are like, that will never happen. It's impossible. I don't think it's impossible, right? It's just a very difficult engineering challenge, but it's kind of amazing what we will be able to accomplish. And once we are able to build a self-replicating robot probe and we send it off to another star system, and maybe it takes it a couple hundred years to get to the nearest star system, and then it arrives, builds copies of itself, those go to another star system. Within a few million years, we will have mapped out the entire galaxy. And of course, this is the Fermi paradox, which is that if this is a thing that we're going to do, right? And if even dumb rocks like Oumuamua or Borisov or 3I Atlas, if just ice and rock can cross the gulf between planets or between star systems, shouldn't we be able to do this? Shouldn't smart rocks be able to make this journey as well? And so it feels this kind of inevitability. And so that if this is something that we will do, then we would expect that other advanced civilizations, the ones that started a billion years before us, will have already done this as well. And yet, when we look out into the cosmos, we do not see any examples of these self-replicating robot probes. So either it is truly impossible and no one can ever, not ever, make a copy, or we're alone in the universe, or there's something else we just don't understand. Dying to play. What are your thoughts on the problem with sending crew to the nearest star? The issue of the rocket equation, physics, lack of gravity. Would they survive with the new planet's gravity? I mean, the problem right now is that we just don't have the technology to go fast. Like, that is what you need, is a propulsion system. Our best propulsion system that is in operation today would still take 10,000 years to cross the gulf between the solar system and Alpha Centauri. And that is just too slow. No one's got time for that. So we need a faster engine. And there are much better ideas, much faster engine concepts in the works right now. You've got fusion power. Maybe you can knock that number down to 1,000 years with fusion power, but that's still too long, too slow. That's why, that idea of a generation ship, maybe you just go slower and you just have people live and die in your ship until you get there. What is your purpose? Your purpose is to survive long enough to make sure that you procreate and then die. And then the next generation will do the same. You're in a prison. You're born into this life and then you will die on this little ship. And that's just that. Like I actually think generation ships are bordering on a crime against humanity when you think about it. So that is the problem. And so really it comes down to, we need to, if we want to send people, we need a propulsion system that can get us there quickly. The only kind of two ideas that we have right now are laser sails, where you fire a laser at a ship and you accelerate it to incredible velocities. The downside of that is that living beings would be squished by the kinds of accelerations that a laser sail would do to get you up to relativistic speeds. And you have no way to slow down. So you're going to zip right past your destination and head off into deep space and everybody's going to die. But antimatter, that has the kind of energy density that's required to be able to both accelerate your spacecraft at a reasonable speed and decelerate your spacecraft at a reasonable speed to arrive at your destination. And so, in some far, far future, we will be better at harvesting antimatter. We will be better at using it and as a propulsion system. And maybe that is what it's going to take. Once you've got that, so, you talk about is it the rocket equation, physics, lack of gravity? So let's imagine that we cracked antimatter rockets and we're able to send people to other star systems in a reasonable amount of time. Let's say we can send a person, a crew to Alpha Centauri in 20 years. So the first issue is they're going to be in deep space in radiation for 20 years. And not just radiation, they're actually going to be going at relativistic speeds. And so they're actually going to be sort of crashing into the particles at even higher speeds. So there's additional risk of just being out in space. And you're exactly right. The lack of gravity. So if you can accelerate your spacecraft at 1G, then you could theoretically accelerate yourself at 1G for half of the journey, turn the rocket around, decelerate yourself at 1G, and your crew would be under Earth gravity the entire time. And maybe you can only accelerate at 50%. That would still probably be much better than just being in weightlessness, because a decade in weightlessness would probably not be good for the human body. But once you get to the new planet, it all depends on what the gravity field is on that planet. So if it is the same as Earth, then you would totally be able to survive on the surface of that planet. But will that planet be habitable? If it has some kind of biology on the surface in the same way that we have biology on the surface of the Earth and has been operating for billions of years, then it is theoretically possible that it would have an atmosphere that you could breathe. And I'm sure, before you send the crew to this other planetary system, you are scanning the atmosphere of this system and making sure that it is totally safe for you to be able to go there. But that is going to be the challenge. But then is the biology even compatible with us? We don't know. So, a lot of this is just science fiction right now. Hopefully, never say never. One day we will come up with the technology to be able to accomplish sending human beings, sending this meat to another star system. That would be incredible. Clive Warren, people keep going on about AGI, but won't quantum computing be more powerful? Quantum computing is just different. So the kinds of things that a quantum computer is good for is very specific kinds of computing challenges. And so when you talk about sort of more powerful, the thing that advanced AI is going to be doing is essentially being able to solve problems, to direct activity towards a goal. And however you get there, whether it's just traditional silicon or whether you're able to, run algorithms that get you in that direction using quantum computing, it all just depends on, can you sort of collapse the possible futures down to the point that you can actually achieve some kind of outcome. And that is what sort of all artificial intelligence is moving towards, is being able to kind of accomplish and achieve outcomes in the universe that we find ourselves in. We think about us as people, right? You have a plan, you have a goal, you have a thing you want to get accomplished. You have agentic behavior. And whether you do that in the sort of more traditional silicon way or whether you do it with quantum computers, there was there's a really great book that just keeps getting more accurate over time. It's called The Age of Spiritual Machines. And it was written by Ray Kurzweil, in the 90s. And he predicted with just stunning accuracy today. Like, he predicts that there would be a computer with the sort of capability of a human mind, but on a supercomputer running by about 2029. And that by 2039, everybody will have these on their desktop. And then by 2049, everyone's desktop will run a mind that is 1,000 times smarter than a human being. And he didn't really think too deeply about what are the philosophical implications of a mind that is 1,000 times faster than 1,000 times smarter than a human being. Like, would it still want us around, right? Would it treat us the way we treat ants or chimpanzees or anything, right? Yeah. But I do recommend, like, read that book. And just, like, he explains this idea, he's not sure where the computing is going to come from. He talks about Moore's law and says, well, he imagines there would be reversible computing. So right now, computing is very produces a lot of heat. But in theory, you can sort of run all of your circuits, and then you can sort of extract the energy and run your circuits in reverse and not have to produce a lot of heat. He imagines 3D substrate, because right now all the chips run in 2 dimensions, but he imagines they could run in 3 dimensions. And he imagined quantum computing and reversible quantum computing. So you imagine all these ideas. Well, turns out all we needed to do was just keep shrinking the size of the circuits to the place we find ourselves today. And we are approaching the predictions that Ray Kurzweil made 30 years ago. And his math was very simple. He just said, I look at the curve, and then I just extrapolate the curve, and this is when on the curve weird stuff is going to happen. So it's a great book. And it's good for the last show of the season. Slow boy fuel pump. Fraser, do you think we have entered a technological singularity? It really does feel like we are starting to enter the technological singularity. Things have felt like they are accelerating faster than I can wrap my brain around it. And I will often spend a lot of time working on stuff that's the cutting edge, the bleeding edge. And there's so many new things that are popping up, so much stuff that's being done, that it's kind of hard to stay on top of it all. And I think right now we're seeing people are becoming more productive coders anyway by using these automated tools. And I think a lot of people thought, they're going to be great for making images and videos and writing. And that was a horrible mistake, right? Like, everyone, I think, agrees now that AI video is hot garbage. AI music, I guess the AI music companies are doing well, but the music they produce is hot garbage. But the code is actually pretty useful. And if they just stuck to code, I think they wouldn't have had the same kind of dilemma. And right now, I think Anthropic said that they're getting like an 8 times speed up in their coding. Now, they could be producing garbage code, who knows? But things will get kind of scary when the AI is upgrading itself, right? This idea of recursive self-improvement. Once we hit that point, things are going to feel like they're going to accelerate significantly at that point. We're not there yet, but it does feel like that's kind of around the corner now. So it does feel a little like we are entering the foothills of the technological singularity. To me, anyway. Ed Skeptic. Humans don't understand consciousness. How are we going to create it in non-living matter? It's actually ridiculous. You don't have to understand how something works to make it, right? Like, there's lots of technologies that we don't understand fully, and yet they do the job, and they don't have to be conscious, right? Like, a thermonuclear weapon doesn't have to be conscious to cause an enormous amount of damage. There's stuff that do things, and they may not have no thinking behind them. It doesn't matter. That stuff is getting done. You don't have to, a car doesn't have to be conscious to carry you to your destination faster than walking. It just has to carry you to your destination faster than walking. So artificial intelligence may never be conscious, but it's going to have a profound effect on our society, and it already is. Keith Romig, I know you watch Digital Circus. Quick question: are the characters in the show just a digital copy of the real person? Is that what they did? They put their likeness into the game, right? So, whoa, all right. So the Amazing Digital Circus is a show on Netflix, and I think you watch it on YouTube as well. And it tells the story of this very strange place where there's this kind of ringmaster MC and a bunch of grumpy avatars who are sent on adventures by this MC. And you sort of learn pretty early on that this isn't just like a weird story in a weird world, a bunch of people doing stuff, that these are all people who are trapped in this virtual reality, and that there is an artificial intelligence that is torturing them, sending them on adventures, having fun at their expense. And it is kind of an anomaly. It's a what do you call it? Anyway, it is sort of like Harlan Ellison, a very famous Harlan Ellison story called "I Have No Mouth, Yet I Must Scream." And if you want to not sleep tonight, go watch some videos on YouTube about the synopsis of "I Have No Mouth, Yet I Must Scream." The gist being an artificial intelligence is torturing people or is punishing people, I guess is a better way to describe it, for being human. It hates humans and is just being really mean to them. And so in this show, you find out that the people are trapped against their will in this virtual reality and are being sent on happy, fun stories while sort of facing the existential crisis of being in this horrific situation. And it's good. It's not great. I don't love it, but my kids are pretty into it. So I guess it really kind of strikes, and it's getting them into more kind of existential sci-fi horror, which I think is great. Having them read, actually, like my kid was like, "Oh, I really like this thing. It's based on Harlan Ellison," and then they read the Harlan Ellison book. So like that, makes a father proud. So what it seems to be in the show is that they jacked into the system and got sucked into this virtual reality, and they can't get out. It's like Sword Art Online. It's like The Matrix. But the computer is making their lives bad. Gadzooks, would you go on Doom debates? I already did. If you go back, search for my name on Doom debates. I already talked to Liron. I was one of the first guests. I was following Doom debates when he had like 1,000 people, and he brought up where is it? Oh, here we go. And Liron brought up the grabby aliens hypothesis, and so I reached out to him and said, "Hey, if you want, like, I don't talk about AI, but my degree's in computer science and I think a lot about AI, but I took but I do report on aliens and grabby aliens and all these kinds of things. So, the great filter and so on. And so I went on the show and we talked about aliens and my problems with the grabby aliens hypothesis and what's my PDoom is 50%. So Scott, you ever try to get on Jeopardy? No, thank you. Paige Potter, how do you recommend we spend our Monday evenings during the hiatus that might still scratch the space itch? Well, so the biggest thing that I can share with you is the smart telescope that I've built. And I'll lay out the entire plan, and so you can sort of tell me whether you think it's a good idea or a bad idea. So the gist is, I've got my various smart telescopes. You got them arrayed behind me, the C-Star and so on. And they're amazing because they're really easy to use. You just plop them down, you point them in a direction, they just stream. And you build up these images on your phone, and it's incredible. But to kind of share the experience with a live audience is just misery. And I have tried. I've tried each of these telescopes. I've tried to figure out a way that I could share it with you. I even had a Celestron, I forget the name of it, First Scope. I forget the name of the Celestron one. That didn't work. And so I started to say, well, what if I built my own? And so I have assembled all of the parts for my own smart telescope. It's a really nice mount, an old refractor that I've got, and a nice color camera. And then it's attached to a Mac Mini, and the Mac Mini controls the whole thing. And it has this interface that I use to be able to show you the night sky. And I think I can even show you what this looks like. Let me see. See if I can do this right now. Okay, let me see if this works. Yeah. So this is the view that we got. So what happens is, so hopefully you can see this on the screen right now. So it's got, I have an interface that I can use to point the telescope at a certain target. And then I can, let me see if I've got a demo mode too, even. Let me see if this works. This would be cool. Does that work? No, it doesn't work. Okay, never mind. Okay, I'll fix that next time. Yeah, so this is the interface, and so I'm picking a target. In this case, I'm picking a cluster in Perseus, and you guys get to watch the image get built up over time, and then we move to a new target, and you get to watch it get built up over time. So that's the cluster in Perseus. We can do the Veil Nebula, which is really cool. So, and so this is kind of like the first part of the idea, which is that I can, and now it's like, it's working really, really well. Like it is now rock solid. I can show the moon. I can show deep sky objects. It happens really fast. It's got really cool animation that shows you where the telescope is looking. You get a view of the constellation, shows you where the telescope is moving to. So that's all cool. And then if you see, there's a space beside me. So my plan is that I'm going to then invite special guests. So other astrophotographers or scientists who are working on some kind of technology, some field of study, or even just celebrities who've always wanted to try using a telescope. And then I have a mode that they can use to just control the telescope. So I can hand over the keys to the telescope to the guest, and then I can be kind of talking to the guest while we're controlling the telescope, and we're either just being silly about space, or it's a serious interview, or I'm talking to an astronaut, or whatever. But we have this, so it's like part education, part interview, part just nerd fest. So imagine like the only way I can sort of describe this, like Hot Ones, right? But we're using a telescope instead of eating chicken wings, if that makes sense. So let me stop that. There you go. Back to me. And the reason I'm telling you this is that I am going to be kind of relentlessly testing this and trying to make this work and figure out all of the bits and pieces. And then once it's all operational, then I'm going to put this thing down at Starfront in Texas. So I'm going to stack up this entire telescope exactly in Starfront. So then you've got, instead of my crappy West Coast skies with very little horizon around me in all directions, with mountains in all directions, it'll be perfect skies, Bortle 1, perfect horizon in all directions, and it'll be incredible. I hope, and it should be fun. It'll be educational, and we should have interesting events, and we'll watch lunar eclipses, and we'll try to do a Messier marathon where we try to find every object in the entire Messier catalog, and all kinds of stuff like that. So that is, we're going to be trying to do that I'm going to do that as often as possible. So I'm probably going to show up later on tonight, like after, like it's 6:30 now. This live stream will end at 7 my time, but probably around 10-ish, I'll be back and trying to make this thing go again. And I'm just going to keep showing up every night that I have clear skies until I feel like this whole system is bulletproof. So that's the thing. That's how I recommend you spend your Monday evenings. But if I'm not live streaming, oh man, there's lots of good stuff out there. You know, TV shows, new episodes of Rick and Morty. You can watch Star City if you haven't already watched that. Yeah. Hemp freedom. If there was one or more universes beyond ours, would we be able to see them? So it really kind of depends on what you mean by behind and universes, I guess. You know, do we live in a multiverse? Do we live in, you know, not just this universe, but are there multiple universes? And there are ways that you can actually have multiple universes in the universe that we have. So imagine, right, if the universe is infinite in all directions, then that you will have sort of repeating circumstances. You'll have another Earth, you have another you. And in fact, you'll have an infinite number of Earths and an infinite number of yous. And so you will eventually have what is the entire observable universe repeated out there in the infinite actual universe. Is that a multiverse? If you wait long enough in time, we could very well have another universe. So that's another possible universe. But the one that you're probably thinking is the one that's sort of discussed in science fiction a lot of the time, where, you know, in Stargate, there's a problem with the Stargate and they end up in this alternate universe where everybody's got little beards, right? Or maybe that's, you know, the mirror universe in Star Trek. So one of the sort of ways to explain quantum mechanics is called the many world hypothesis. And that is that just, you know, right now, when there are particles and the particles in decay, you sort of think about the Schrodinger's cat problem, right? That, you know, you put this cat in a box, you put this particle in with the cat, you run the experiment, it either decays or it doesn't, and the cat is in this superposition, and you open up the box and then you see whether or not the cat is alive or dead. And that is the sort of the thought experiment. And in the many worlds hypothesis, instead, the universe splits into two universes, one in which the cat is alive and one in which the cat is dead. And so every time a decision gets made in this universe, it splits off another universe that is very real, like is as real as this universe. You happen to be in the universe that you're in, which is this sort of winding line through all of the decision tree that could have been made. But we wouldn't have any way to access or see or view that other universe. Another possible way that you could have multiple universes is there's this theory called inflation, which is, you know, there's a lot of observational evidence that this is the case, that early on in the history of the universe, there was this sort of rapid expansion of the universe, and we've got a version of it that stopped inflating just moments after it began. But it's believed that there's other places in the universe where this, or in the larger universe, where this inflation is still happening. And that these universes are going to kind of overlap with each other, and could sort of, where they overlap, you get this kind of mess. And so in theory, if there were other universes that we were colliding with, that we might actually detect them, or maybe the collision would happen at the speed of light. And so the moment we experienced it, it was already over. So, you know, there's a lot of sort of proposed ideas for how there could be other universes, and some we can hope to observe, and others are just beyond our ability to observe at all. Any chance of a Jeremy Hansen? Yeah, that'd be great. You know, Jeremy Hansen is a Canadian astronaut who was on the Artemis 2 mission, and, you know, busy guy, but now hopefully his time has gotten a little easier. So maybe I will put a call out to Jeremy Hansen. That'd be great. Oops. Okay. Avon, did you vibe code the software side yourself? Yeah, it's vibe coded, totally vibe coded. You know, my programming ability is not that good anymore. Nomad 77. When will the AI do my dishes? That is the important question. Yeah, I think there's a lot of justified hate for AI right now. Like, there's a lot of environmental issues and sycophancy and impact on human psychology and all of this kind of stuff. But I think if it could get to the point where it could do our dishes, I think a lot of people would be on board. I think that's it's not going to be genuinely useful until it literally takes away the need to do dishes. If you never had to do dishes again for your life, that there was just a robot that was cleaning up after you. No, if you never had to clean your house ever again, and you weren't having to hire a maid, you just your house stayed clean. The robot maid came out and cleaned your room, cleaned your house, washed your dishes, took out the trash, cooked your food. That'd be pretty great, I gotta say. Dad, hello, can you chat here? Yes, you can. No, chatting is forbidden. Yeah, this is live. This is actually live right now. Unless you're watching this after the fact, and then it was live, and now it's not live. So you can leave a comment, but you can no longer chat. But if it is in between 5 p.m. and 7 p.m. Pacific Daylight Time, then this is live. Casey Villain, have we found evidence of plate tectonics on any bodies beyond Earth? Do we have any idea about how rare this geological phenomenon is? Do we have ideas about the role of tectonics in habitability? No, yes. Moving on. No, I'll give you an answer. So plate tectonics is unique on Earth. This is this idea that the Earth is broken up into these separate plates where they are floating on top. So there's sort of like the lightweight continents are floating above the heavier ocean plates. And so you get the subduction and you get this, material going underneath other parts. You get earthquakes and all that and lava and all that kind of stuff. But you get this refreshing of the material on the surface of the planet. And it appears vital for the habitability of planet Earth. And that if you don't have plate tectonics, you have a place like Venus. And so the Venus is called a stagnant lid, which means that it is this sort of entirely probably solid shell around the mantle on Venus. And you don't get the plate tectonics that we have on Earth. And then instead, it's possible that you just get the entire surface of Venus just inverting itself from time to time. Like so much pressure, so much heat builds up, and the whole thing just sort of flips over, liquefies. It's a mess. And we don't see plate tectonics on Mars, and we don't see it on Mercury. And so those are the only places that we can compare here in the solar system. We see something kind of like plate tectonics when you look at some of the icy worlds out there. You look at Europa, you see these cracks on the surface. You look at Titan, Enceladus, Ganymede. So it might be that you have a very similar process on these ice worlds, but it's ice floating on water. But we don't have any evidence. We don't know what's out there around the universe. It could be that plate tectonics is very normal, that there's a certain size of planet, a certain distance from the star, certain composition of the atmosphere, and that gets you plate tectonics, and there's one in every solar system. But it might be that it's incredibly rare, that there is some very specific recipe for the conditions on planet Earth that allowed us to have these plate tectonics. Is it important for life? It appears to be vital. Again, just look at Venus, right? Venus sucks. And part of it is that Venus has no way to sequester the carbon in its atmosphere. On Earth, we have life. Life forms biology. The biology sequesters carbon onto the surface of the planet. You get geology that is subducting, that is essentially pulling that material under other plates on planet Earth and sequestering that carbon away from the surface. And so you have this regulation of the amount of carbon that's available in the atmosphere and the amount of global warming, temperature rise that you get. On Venus, that process maybe never happened or stopped at some point in the ancient past. And so the carbon dioxide just built up and built up in the atmosphere from the outgassing from volcanoes, right? You've got volcanoes are outgassing, and then nothing is soaking it back up again. And it just keeps building and building and building. And we actually talked about this earlier in this episode, how great those volcanic gases would be if they would build up on Mars. And yet on Venus, it's too much, right? You want to be able to dial that back. So you want the perfect amount. And it could be that just this process of tectonics, constantly sequestering, you get this cycle that's going on in the atmosphere of the planet and the surface. And that is what's necessary for habitability. Now, we don't know, and the universe has a way of showing us that things can be weirder than we had ever expected and still work. And so it might very well be that, in fact, we don't need plate tectonics, that there is a version of Earth that's at the right distance, and there's other mechanisms that sequester the carbon and allow for the cycle to happen that don't require plate tectonics. But it really does look like the plates are key. Could be that we have a large moon that some another buffer 641. Yeah. I hope it saves. Peach Potter, what is the most, I can't believe this is my job moment you've had covering space? Oh, wow. I mean, so many. I mean, just like I experienced this kind of background level of, I can't believe this is my job. Like, that's just my day-to-day experience is I look at science papers. I look at the ones that kind of strike my fancy. I then hand those off to writers, many of which who have advanced degrees, and then stories that I'm interested in reading pop out the other side of this process. And then I get to talk to people, and I get to share a view with a telescope. So that is like just the background, and I'm like, I really feel grateful that I'm able to have this job. And I think there's a lot of people who are like YouTubers and stuff, and they get burned out. And you see this happen. Like, think about all of the YouTubers that you used to watch. They were successful. They were making money. They were at the top of their game. And yet it was just like they couldn't handle it. They didn't like it. And I think part of it is that you've just you gotta enjoy the work. And you can't let yourself get kind of captured by the forces that are always trying to push you in places that are going to make you feel burned out. There's always this tendency towards making things more hyperbolic, more, So, well, I've been watching all the coverage of the steam machine, which is this, I know this is like totally divergent rabbit hole, but I'll bring this all back around together in the end, I promise. So the steam machine is this, new system from Valve. We were all excited about it. Suddenly you had a console that was going to play your Steam library on the television. Maybe it was going to cost about $700, $800. Incredible. Now this thing is actually more like $1,100, more like $1,400, $1,500 when it's fully kitted out. And it still will do this job, but it's a lot more expensive, and people are sort of coming up with cheaper variant alternatives than the more expensive version. But if you look on YouTube, it is like the sky is falling. Everything has gone to hell. That this is the apocalypse. That the worst possible outcome that could have ever happened to humanity is now unfolding, and it's Gabe's fault. And the fault is not on Gabe, the fault is not on Valve. The fault is on the AI industry that is gobbling up all the RAM and all the processors and all of the video cards and all of the hard drives and all of the SSDs, and leaving us in this place where we have to just beg for scraps to be able to put together a PC that will just play our video games. So but the tendency is to be hyperbolic, because that is what drives the clicks. That's what makes your job make you money. And I just resist it. I'll do, like, even when I started to do interviews, they didn't get any traffic. They didn't get any, I don't care. I enjoy them. And that is the part that like when I am interviewing an astronomer, I am just in bliss. I am having so much fun asking my questions to this person, satisfying my curiosity. It, like, if I would get electric shocks as my compensation for doing interviews, I would still do them, because I have so much fun conducting those interviews. Fortunately, I don't. I just get, mediocre traffic and a fraction of the views, but I really enjoy them. And then that's the baseline. And again, I feel really, really grateful. And that's why I think I've been able to do this job for 27 years, right? Is I just keep going after whatever I find to be the most fun. But then you have the moments where you do have to literally pinch yourself, because, I've interviewed multiple Nobel Prize winners. I've interviewed astronauts. I've talked to astronauts while they're in space. I've watched rockets. I've watched a rocket launch. I've been to the Jet Propulsion Lab, Kennedy Space Center. I've met astronomers around the world in person. And that is great. And again, you're just, when you send out an email to somebody who you can't believe they would ever want to talk to you, and they're like, yeah, that sounds good. And you get them on the screen and you're talking to them. It's crazy. It's amazing. They wrote a book that you loved and you're talking to them. It's amazing. So, so there's like too many to like, too many answers. I think the most surreal one that's ever happened to me, and I think you can still find this on YouTube, is when the Interstellar movie came out, they were doing a press junket. And so they had, I think, Anne Hathaway and Matthew McConaughey, and then they had an astronaut from NASA and I think it was an astronomer. And then they invited me online to be in the middle of their hangout. And so I was answering questions about space to Anne Hathaway and Matthew McConaughey about the Interstellar movie, which was pretty surreal. And that was definitely one of the, I can't believe this is my job moments. Not anybody paid me for that, but still, yeah. Could you give us a long closing rant, topic of your choice? The rants, they just, like, I cannot predict. I cannot summon a rant. The rant has to be natural, has to just happen, has to trigger some kind of breaking point in me, and then the rant happens. So I apologize, church discography. If I could rant, I would, and maybe I still will. We don't know. There'll be a rant or not. They happen. I can feel when I'm going to rant. That's all. It's sort of like, I can feel like I'm about to turn into the Hulk. Henry Warren, still no 3D printer, Fraser. No 3D printer. I've been just nerding out about my telescope. And so once I feel like I got my telescope locked down, then, but there is like a crossover, because I've got this just mess of cables and computers and stuff sitting around the base of the telescope. And then every time I put the telescope out to do observing, I have to pick all this junk up and carry it in a little basket. I'm like, oh, it'd be great if I had like 3D printed a little shelf, and the shelf had the exact footprint for the Mac Mini, so it would hold it tight, and then I could strap it down, and then I could have a place to put all that, and that would be perfect. I could 3D print it. I could learn 3D software to design the shape of the thing. And then they're like, whoa, no, Fraser, no. Finish, carry them around in their little bucket. That's what it's going to take right now until you get this telescope operational. So I think the next rabbit hole will either be the 3D printer, which, I've gotten some great answers from people. or a microscope. Because I'm like, I'm into gardening, and I would love to be able to look at what's inside my garden under the microscope. And just microscopes are cool. So I think that's probably next, is a microscope or a 3D printer. Man, 3D printer would be so cool. Well, there you go. CeeLo is saying 3D printing can take over your life, no regrets. Okay, well, there you go. Carolyn, there's some cheap handheld microscopes. Yeah, but I don't want the cheap one. I want the good one. That's what I want. I want the one. And I've had a couple of patrons who I've interviewed, and I've asked them, like, what's the good microscope? And you're probably looking at about $1,000 to get something that you'll feel really happy with. So, yeah. Caver, how are your bridges? Bridges are great. We're using the bridges like crazy. We're what you're not seeing is that we are clearing a bunch of the trees, thinning out the forest. And so I had to go back and forth over all of these bridges to try and drop a bunch of trees. But so I look like I'm doing a lot of space reporting, but actually I'm doing a ton of work out and outside. I'm a lumberjack and I'm okay. Zappan, rant on Starlinks, ruining your telescope views. Okay. Yeah. So we've been doing the live streaming of the space, and I'll show you an example here. Let me see if I can find you some examples here. Sure. Here we go. So I don't know if you can see it. There's a satellite trail in the upper left of this picture. Where's another one? Here's one at the top. Here's one across. So I would say about a third of the pictures that I take have a satellite trail. Now, I can't say that they are absolutely caused by Starlinks, but is it weird that now there are 10,000 Starlink satellites and there were 2,000 regular satellites? So, mostly there are Starlinks. They're Starlinks. So the solution is, because originally I was like, well, you know what? We're just going to let these trails remain, and this will be a talking point. That we'll be taking our picture and we'll be like, great, beautiful frames, and then satellite trail. I'm like, oh, and then we'll all complain about Elon. We'll shake our fist and complain about satellite trails, and then it'll just be baked in. But then you get like another one, and then you get another one, and after a while, I'm like, okay, this is too much. So there are algorithms that will remove satellite trails. And so I've been able to implement the algorithm that removes the satellite trail. So what's going to happen is you'll see the satellite trail appear on one frame, and then it will be removed on the next frame. So we'll have 30 seconds to complain about a satellite trail, and then it'll be gone from the image as the image continues to build. But when you think about the level of satellite trails today, this is 10,000 satellites, 12,000 satellites, wherever we're at right now today. SpaceX's original request was somewhere in the 40,000 satellite range, and they're on their way. But now they've requested or expected that it's going to be in the hundreds of thousands, maybe even millions of satellites. And that's just one company. Now you've also got Amazon with their constellation. The Chinese are building theirs. The Russians are building theirs. Other nations are going to need satellite infrastructure because it's like part of your society now. It's sort of like this basic service that's going to be required. Every country, like, will a country depend on a US-based internet provider? No, everyone's going to need their own satellite provider. So there are going to be millions of satellites in low Earth orbit around the Earth. So it's bad today, but just you wait. Like, it is like, this is, I'm trying to think if there's a thing that people can remember the day, remember the time. So there will be a time when people remember with fond nostalgia when there weren't just millions of satellites in the sky. And like, obviously, like right now, when you look up in the sky, even in dark skies, you can see a couple of satellites, but they're not everywhere. And it may get to a place, it may never get to a place where they're everywhere because they're too faint for you to see. But in a telescope, you can see them. But they cause this diffuse sky glow. So every satellite that's up there, even if you can't see it, it is causing a little bit of glow. It's causing a little bit of light pollution. And bit by bit by bit, they're all going to add up. And so right now, you can live in the city and you don't see any stars, but that's your fault. You chose to live in a city. You can move to a place that has really dark skies and suddenly you can see the Milky Way and you can see all of the incredible stuff that's up there. Well, soon that will be taken away from all of us because of all of these satellites. So this sucks. And at the same time, people need communication. And I don't think it's fair for us to say we shouldn't communicate, right? Do we run fiber optics? Is that the solution? Do we lay cables through the ocean? Do we set up Wi-Fi towers? I think if we really thought it through, fiber optics would be the way. But then you still wouldn't be able to have so if you couldn't have a cell phone, I guess that's the choice, right? Would you prefer to have cell phones or the night sky? That's probably sort of where we're getting to. So, yeah. All right. We've reached the end of this season of my Monday question show. So, thank you everybody for hanging out with me all this season, for the last 10 months of live streamed episodes. Thank you to the moderators. I see Zapfan is here, who was given a sort of less duty a couple of months ago, which has been great, but it's an absolute pleasure to have you and the other moderators that are here. Thanks in advance to Chad and Anton. We're going to have to edit this nonsense, and we'll still be editing madly over the summer. And yeah, this is so much fun. But I hope you appreciate that I am enjoying this, hopefully as much or more than you are. I really enjoy answering people's questions, genuinely. And if I didn't have this venue, then I would just be randomly finding people and finding out if they have any questions for me to answer. So thanks everybody. Really appreciate it. We will see you live. Well, tonight probably, but we'll see you back at the beginning of September. All right. Thanks everyone. See you in 2 months.